Okay, morning guys. Another gorgeous day in the garden, so I thought I'd stay outside for this one. Today we're going to look at bond energies and calculating bond energies. Now, I warn you in advance, people generally find this quite difficult, so stay with it. I will ping you the PowerPoint as well as this video because I think time spent going through this is seldom wasted. There is a worksheet that looks horrific, but once you get the hang of it, it's not too bad, right? And it's worth bearing in mind that effort will yield rewards on this. Okay, nobody got this quickly, I didn't. So, I'm going to go through it very quickly, what you need to do and how we do it. Right, so you should be able to calculate what we call the energy transferred in chemical reactions using the bond energies. I'll explain what that is and why that works. And then to be able to use the value for delta H, the energy change, to say whether reactions are exothermic or endothermic based on whether they have negative or positive values. And if you've watched the previous videos with activation energy and the one before to do with exothermic and endothermic, this should be familiar. So this is kind of putting the icing on the cake. So let's get started, if I can make the tech work. Right, let's go back to our friend Lego again. We talked about this in activation energy. Here's my Lego creator set. It's an awesome bit of kit this. When we started out, we built the underwater robot. And then from that, we want to then build the underwater probe. Now, that's not that simple, is it? You can't go from one to the other directly, because what you have to do first is you have to break it apart. So what we have to do is break open each bond, each particular link between Lego blocks. We're not breaking the Lego blocks, we're breaking the links between them, and we have to put energy in to do that, and then we put them back together again and reform them. Now if you think about that, it's going to take exactly the same amount of energy to pull each Lego block apart for different types of Lego. So if you've got two of the little two-piece ones, they're going to take less energy to break apart than two of the big sort of like 4x2 ones, because the bonds aren't as strong between them. And we can quantify this. Right, and that's what we're going to do to calculate the energy change here by working out what the energy change of those two processes is. So go back to the energy profile diagram we looked at in activation energy. Okay, here's my robot. What I've got to do is break open all those bonds. And if I add up the bonds and I know how much energy is required to break each of them, I can work out exactly what that energy jump is. What I can then do is work out what the energy given out is by reforming bonds. Okay, Lego doesn't give out energy in the same way. It doesn't have the same attractive forces. If you think about Lego as being magnetic, for example, that might be a better example. Pulling it apart takes energy, putting it together again releases energy. And so the energy given out when they reform, again, I look at the number of Lego pieces clipping together, so the number of bonds between them, and there's this, the energy size, or the magnitude of each of those bonds. I can then calculate the overall energy change, or delta H. So this is quantifiable. Okay, if I've got numbers, and you'll be given numbers in the exam, you can calculate the energy changes involved. So let's give an example of this. Okay, I'll give you a couple of examples. Right, now, there are some definitions here. They're all on the worksheet. You haven't got to copy anything down. This is about calculating and doing. It's not about rote learning. So, how we calculate bond energy or energy changes, we use the bond energies. Now, a bond energy is the amount of energy needed to break apart a mole of a particular bond. What is a mole? It's a big number. We'll do moles much later on, but it's just the opposite. If I said to you 1 piece of Lego, a dozen pieces of Lego, a billion pieces of Lego, to break apart one Lego bond or a million Lego bonds is going to take different amounts of energy, so we use a mole. It just means 6.02 times 10 to the 23 of that type of thing. Why do we pick that number? Going nowhere near that today. It's another lesson. So you'll be given bond energies. Ignore the mole bit. You don't need to worry about it. So this is what you do. First things first is you add up all of the bond energies for all of the bonds in the reactants. So look at the reactants, how many bonds are there, add those bonds up, and add the bond energies together. That's the energy in. Then you look at the bonds in the products, and you add up the bond energies for all the bonds in the products. That's the energy out. So this is a three-stage calculation, right? Stage 1, bonds of the reactants, how many, and what's the number value of each bond. Step 2. Look at the number of bonds in the products. What's the energy of each bond? Add those together, that's energy out. Step 3, the change in energy is in minus out. The energy in minus the energy out. Okay, the maths is simple. Getting your head around it is difficult. Okay, this is what I would say, not difficult, but it's hard. The maths is trivial. but getting your head around it is going to be a bit of a challenge. So take your time. Let's give 2 examples before you can have a go at some yourself. Right, worked example 1. What I've got here is a reaction between hydrogen gas and chlorine gas to make hydrogen chloride gas. Okay, if you dissolve hydrogen chloride gas in water, you get hydrochloric acid. Right, but this is how we make it. So if we have a look at that, this is the equation here. I've got HH, so there's a hydrogen bond there, an HH bond. That line in the middle is the bit I'm interested in. I'm not so worried about the atoms. The line in the middle is a covalent bond. It's the thing holding them together that I've got to break. Then there's a molecule of chlorine, a ClCl. So there's a ClCl bond there. I've got to break that bond as well. And then at the end, they're going to reform to form HCl and HCl. So there's 2 HCl bonds. So it's an exam. I'm given the bond energies. There they are. Okay, the units are kilojoules per mole. Don't worry about it. Just put that unit on at the end. Don't worry about what it means. Okay, but kilojoules per mole, 1,000 joules per mole of that particular type of bond. So, to break hydrogen-hydrogen bonds, it takes 436 kilojoules. To break chlorine-chlorine bonds, it takes 243 kilojoules. And to make hydrogen chloride bonds, it's 432 kilojoules. So, step 1, what do? Energy in. So energy in, I've got an HCl, I've got a ClCl. So I'm breaking that bond and that bond. So think of it a bit like algebra. What's the numerical value of that? Well, the numerical value of that is 436, so there it goes. Add, what's the numerical value of that? Well, that's chlorine, chlorine, so that's 243. 436 plus 243, 679. Okay. Step 2, energy out. So this time, what's being made this time, it's 2 lots of HCl. So there's 2 hydrogen chloride bonds there. So there's 2 lots of HCl. For some reason that's capitalised. It shouldn't be. Apologies for that. So 2 HCl's is 2 lots of 432. 2 times 432 is 864. Right. What do I do next? Final stage. The energy change, delta H, is in minus out. So energy change is in minus out. 679 minus 864 is minus 185 kilojoules per mole. The delta H value, or the energy change, is negative. If it's negative, that means it's exothermic. Okay, let's look at a second example before I let you have a go on your own then. So, worked example number 2. Hydrogen bromide decomposes to form hydrogen and bromine. So, got 2 HBRs which make H and BrBr. Okay, so hydrogen bromide makes hydrogen and bromine. So let's look at the bond energies for this. So what's the energy in? Well, the energy in this time is I've got 2 lots of that line. Okay, there's 1 per molecule, there's 2 molecules. So that's 2 lots of HBr. The HBr line is 366, so 2 366 is a 732. Step 2, and please, when you do this, lay it out like this. Okay, working is your friend. People who skip working make mistakes, right? And it helps you learn it by doing the working because you're thinking about each step carefully. The energy out then, this time I'm making an HH bond there, and I'm making a BrBr bond. So an HH bond is 436, a BrBr bond is 193. So HH plus BrBr, there you go, gives us 629. So step 3, the energy change is in minus out. So in minus out, 732 minus 629 is plus 103 kilojoules per mole. This time delta H is positive, which means it's endothermic. Now, if you remember, when we looked at exothermic and endothermic, decomposition reactions tends to be endothermic, and lo and behold, this is a decomposition and it's endothermic there. So, here we go. Here we have some questions on the worksheet. There's a bunch of bond energies at the top there for you to use. Calculate the delta H for each of those, or the enthalpy change. Enthalpy is a word that crops up, right? It's an A-level hangover. It just means heat energy. If you see bond enthalpy, I use it a lot. I shouldn't. I should use bond energy. You're going to calculate the energy change for each of these. So, a couple of things to note, right? There's lots and lots of different bonds here, so be really, really careful when you ever go on the worksheet. Some of these bonds are double bonds. You can't see the word double bond because some stupid face is in front of it, but that doesn't matter. So this is a carbon-carbon double bond. This is a nitrogen-nitrogen double bond. Some of these are triple bonds. This is a carbon-carbon-carbon triple bond. This is a nitrogen-nitrogen triple bond. So just be careful when you look at bonds. This, for example, here's a double bond. If you see one, then use the right number for it. But you will find the same numbers crop up all the time. So, what are you going to do? For each of these, identify the number of bonds. Step 1. Work out the number of bonds of each. Add up the energy change for the bonds of the reactants. Step 2. Add up the energy changes or the bond energies, for the product. Step 3. Energy changes in minus out. Number 1's done for you. It's the worked example. So do have a go at it, but you can check it step by step. The whole point of this PowerPoint is it's got that on there already. Number 2. This is a bit more complicated. To help you, when we look at the bond energies, you're counting the lines. So in this one here, I've got a C double bond C bond. There's one bond there of reactants. I've got one. I can't make my arrow work. Here it is. 1, 2, 3, 4 CH bonds there. So you can do 4 times CH, and then you've got an F single bond. Again, my cursor's gone in the bright sunshine. Okay, so when you are adding these up, each line is a number. Don't worry about the elements so much. Each line is a number. Okay, right. If you have any problems, please give me a shout. You know how to get hold of me. It's crumb@tahs.net. I will ping you the answers later on. If you are struggling with this, don't worry, you are by no means alone. Okay, but practice, practice, practice. It will help. Okay, once you've got this clicked in your head, it will become very, very easy to do. Sorry, I'm just checking the timings. But in the meantime, have fun, have a good go at it. If you're stuck, please give us a shout. Do persevere. I promise it will pay off. Okay, best of luck, guys. I'll see you all soon. As soon as I can find out how to pause it, I'll do just that.